making Newton come to life, making yourself instantly younger, or finding your own photo from thousands of photos. It all comes from CNN, the convolutional neural network that gave machines eyes. Even today, in Sora, Stable Diffusion, and every photo app, CNN's convolutional concept remains the core of visual AI. So how does it actually work? And why, after decades, is CNN still working in the front line of vision AI? To find out, we go back where it all began, a cat. Act 1, the history. 1959, two scientists, Kubel and Wiesel, peeked into a cat's brain. Some neurons only fired at edges. Vertical, horizontal, diagonal. That's the birth of local receptive fields. Basically, each neuron only looks at a small patch at a time, like scanning the image piece by piece to spot features. Decades later, Young LeCun coded DeathSpark. LuNet was born, a CNN that can read handwritten digits for banks. Congrats, AI just got its first job. Then came 2012. AlexNet dropped. Trained with GPUs, crushed ImageNet. Accuracy skyrocketed. Deep learning officially went viral. From that day, CNN ruled vision like a king, until a new challenger entered the arena, the Vision Transformer. Act 2, from pixels to patterns. Let's see how this legend actually sees. Let's build a CNN to tell cats from dogs. Here's the whole pipeline in one line. Input image, several convolutional plus activation plus pooling, then flatten, fully connected, then output. Let's break it down. The first star player, the convolution layer for feature extraction. Machines don't see fur or eyes. They only see a giant matrix of numbers, values from 0 to 255 representing brightness. For color images, there are actually 3 channels, RGB. So for AI, an image is actually a 3D block of data, a tensor of size height times width times 3. And here's where the magic begins. Each convolution layer turns pixels into meaningful features. Layer 1 extracts edges and color gradients. Layer 2, corners and textures. And around layer 6, it can extract eyes, ears, and small parts of body. The deeper we go, the more abstract it gets, until entire poses, expressions, shapes are encoded into high-level feature vectors. Then comes the fully connected layer, which weighs these features, deciding what truly matters. Finally, the classifier makes the call. 95% it's a cat. Inside the convolution layer, how machines see. Each convolution layer has dozens to hundreds of filters, tiny 3x3 or 5x5 matrices called kernels. To be precise, every kernel is actually 3D because it spans across all color channels. We'll dive deeper into that in a moment. Now each kernel slides over the input feature map from previous layer, computing how well each small region matches its pattern. Of course, in the first layer, that feature map is just the original image itself. You can think of it like holding a magnifying glass, scanning the image pixel by pixel, asking, does this patch look like my filter pattern? Example, here's a kernel to detect vertical edges. To make it simple first, we'll use a grayscale image. Small numbers means dark areas, large numbers, bright. And the kernel slides over the image, computing the convolution, multiplies and sums each value within each small region. And here we write the result onto the corresponding pixel for visualization. And here is how it works. See this 3x3 yellow patch? Now we drop our 3x3 filter right on top of it. And each spot multiplies its matching pixel, then we sum everything up. So the equation is like this. And the result is 20. That's the number on the corresponding pixel on the output feature map. And do this across the whole image, then you'll get a new feature map that looks like this. Easy, right? Just some multiplications and additions. You can see, when the filter hits the region that has a strong light to dark contrast, the output spikes, meaning vertical edge detected. But if the region is flat, the result stays near 0. No contrast, no edge. Okay, what we just saw was grayscale, one single channel, but a colorful image has 3, RGB. So the image is actually a 3D tensor, height times width times 3. That means each kernel must match this shape too. So a cube, 3x3x3. The 3 in depth corresponds to the 3 color channels. During convolution, it works like this. R to R, G to G, B to B. Multiply, add, combine. Then for each pixel, we add up all 3 values from RGB into one final value. So in the end, every kernel produces one 2D feature map. Code will be like this. And that's just one kernel, and you can see each layer has dozens or hundreds of kernels, each focus on a different feature. So if a layer has 4 kernels, you will get 4 feature maps, stacked together into an H by W by 4 tensor, which is the output of this layer and the input to the next. Since each layer builds on top of the last, so the next layer's kernels have to match this step. So we need the depth to be 4, 1 channel per previous feature map. These are the 64 kernels of the first layer in AlexNet. Some spouting vertical lines, others horizontal, diagonal, or color gradient. And the next layer starts combining them, edges from corners, corners from shapes. And soon, ears, eyes, and nose come together into a face. You might be thinking, wow, these filters are genius. Who designed it? Here's the twist. Nobody did. They are learned during training. We'll get to how soon. Here's what a convolutional layer looks in code, using 32 kernels, each 3 by 3, and apply the ReLU activation function. This ReLU is applied to every number in the output feature map, the whole tensor. If the value is negative, set it to 0. If it's positive, keep it. This adds nonlinearity, so the network can learn complex nonlinear features. Next, the pooling layer. Downsampling. Problem: feature maps get huge. Too many details, too much noise. The fix: max pooling. It keeps only the strongest signal in each patch. Result: feature maps shrinks in size. Information gets denser, more robust. Even if the cat moves or blurs, CNN can still detect, yep, that's a cat. Step 3. Flatten. Turn the 2D feature maps into a 1D vector. Step 4. Fully connected layer. All those features, edges, textures, ears, noses are now combined and weighted to make decisions. Example: pointy ears plus whiskers plus fluffy fur is a cat. Round nose plus goofy face is a dog. The fully connected layer gives each class a score. We call it logits. Example: cat 2.3, dog 1.1. Step 5. Output layer. Finally, the softmax function converts scores, the logits, into probabilities. Example: cat 0.95, dog 0.05, which means the model is 95% confident it's a cat. If it's a binary classification, use sigmoid instead. Output closer to 1, it's a cat. Closer to 0, not a cat. By this point, the CNN has completed its full loop, and at each step, information evolves from pixels to patterns to understanding and decision. Now you may wonder, how big are these networks? The very first LuNet had just about 60,000 parameters. Then came ResNet, tens of millions. By ConfNext, we are talking about hundreds of millions. But if you're just doing cat versus dog, few million parameters is plenty. Act 4. How CNNs learn. We know that the kernels are learned automatically during training. They are also part of the network's weights. So how does the training actually happen? It's the same classic deep learning loop. Compute loss, compute gradients, update parameters, then repeat. And the goal of training is to learn these kernels. At start, every number inside the kernels are random. Through training, we gradually adjust them into meaningful patterns. Step 1. Forward pass. Every time the CNN sees an image, it runs a full pass and outputs a guess, cat or dog, with probabilities like 0.7 cat, 0.3 dog. Step 2. Compute the loss. If the image is an absolute cat, but the model predicts 0.7 cat, it means the result is pretty close but not perfect. We want it to be more confident that this is a cat, so we measure how wrong it is using binary cross entropy. Here, smaller loss means better guess, very close to the correct answer. Big loss means trash. Step 3. Backpropagation. Now comes the reflection part. Which kernel messed up and how do we fix it? We want to adjust every weight W, which is the numbers inside each kernel, so that next time the prediction gets closer to the truth. So we compute the gradient, how much the loss L changes if we tweak each kernel a little bit. If this gradient is positive, that means the weight made things worse, so we reduce it. If it's negative, then weight helped, so we strengthen it. Step 4. Gradient descent. Once we have the gradient, we move the weights slightly in the opposite direction. Here, eta is the learning rate, basically how big each step is. And then we repeat the forward pass again with the new updated weight. After thousands of rounds of see cat, guess, correct, and repeat, the filters start detecting fur, edges, eyes, and CNN finally understands cats. Act 5. From CNN to Transformer. So, after Transformers took over the world, what happened to CNNs? They didn't die, they evolved. Example 1. CNN plus Transformer hybrid. CNN extracts local details from pixels and encodes them to vectors. Transformer then uses self-attention to understand global context. Why use a transformer then? Imagine a picture of a cat catching a fish. CNN can see the cat, the fish, the paw, but not that the paw and eyes should face the fish. So it might draw a cat catching a fish while looking at the wrong way. Transformer links it all. Eyes, paw, fish, making the scene coherent. So CNN sees the trees and Transformer sees the forest. By the way, there's a new way to see images beyond CNNs. VIT, the Vision Transformer. No more sliding kernels. It chops the image into tiny patches, treats each as a token, and feeds them straight into a transformer, reading the picture like a sentence. Example 2. CNN as UNet inside diffusion models. In Stable Diffusion and DIT, CNN appears as a UNet structure. Encode on the left, code on the right, with skip connections to keep the details. So CNN handles the structure and UNet rebuilds the image. So CNN didn't really disappear. It became the visual neural system inside modern AI. From cat-dog classification to multimodal generation, we deep dived into CNNs with real math, real code, and zero fluff. If this episode is fun and made CNN finally click for you, drop a like, comment your aha moment, and share with a friend who is still afraid of convolutions. If you are also wondering about the related topics, click this video for Transformer and this one for multimodal. This is Taijin, turning hardcore tech into sweet little desserts. See you in the next one!